Hello, everybody. Today I am going to talk about attention mechanism overview, which is at the core of LLM. Let's say you want to translate an English sentence, "The cat ate the mouse," to French, "Le chat a mangé la souris." If you were to translate this sentence, "The cat ate the mouse," to French, one of the architectures you could use would be an encoder-decoder model. But sometimes, the original sentence might not perfectly align with the translated sentence at each time step. Here's an example. Take the sentence, "Black cat ate the mouse." In this example, the first English word is black. The first French word is chat, which means cat in English. How can you train the model to focus more on the word cat instead of the word black at the first time step? To improve the translation, you can add what is called the attention mechanism to the encoder-decoder. Attention mechanism is a technique that allows a neural network to focus on specific parts of an input sequence. This is done by assigning weights to different parts of the input sequence, with the most important parts receiving the highest weights. The weighted sum of the input sequence is then used as the input to the next layer of the neural network. In a traditional RNN encoder-decoder, the model takes one word at a time as input and updates the hidden state and passes it on to the next time step. Only the final hidden state is passed on to the decoder for processing. An attention model differs from a traditional sequence-to-sequence model in two main ways. First, the encoder passes a lot more data to the decoder. Instead of just passing the final hidden state number 3 to the decoder, the encoder passes all the hidden states from each time step. This gives the decoder more context beyond the final hidden state. The decoder uses all the hidden state information to translate the sentence. Second, an attention decoder takes an extra step before producing its output. To focus only on the most relevant parts of the input, the decoder does the following. First, it looks at the set of encoder hidden states that it received. Each encoder hidden state is associated with a certain word in the input sentence. Second, it gives each hidden state a score. Third, it multiplies each hidden state by its softmax score, thus amplifying hidden states with high scores and downsizing hidden states with low scores. Let's now connect all the pieces together. Before moving on, let's define some notations. Alpha represents the attention weight at each time step. H represents the hidden state of encoder RNN at each time step. HD represents the hidden state of decoder RNN at each time step. The inversion of the black cat translation is clearly visible in the attention diagram. And 8 translates as two words, à manger, in French. We can see the attention network staying focused on the word 8. During the attention step, we use the encoder hidden states in the H4 vector to calculate a context vector A4 for this time step. This is a weighted sum. We then concatenate H4 and A4 into one vector. This concatenated vector is passed through a feed-forward neural network, one trained jointly with the model. The output of the feed-forward neural networks indicates the output word of this time step. This process continues till the end of sentence token is generated by the decoder. This is how you can use attention to improve the performance of the encoder-decoder architecture. Thank you so much for watching, and see you in the next video.